All righty, finally. How is everybody? Everybody good? Cool. Sorry, I was a little bit late this morning, but I was helping Audrey prepare for her Murdoch talk on Friday, so going through it one last time. So, do we have any questions before I start? Second to last week surgery tomorrow, so I hope we're all stoked and excited for that. Your exams are next up on my grading list. I may get a little time to work on that today. I don't know. I have to report a lecture for you guys on Friday. What I'm thinking that I will do for Friday is we'll see how far I get today. And then I'll probably will just finish up this topic in the recorded lecture. And so, you know, likelihood it will be a shorter than normal lecture. But that way, when I come back on Monday, I can just start on the urinary system. That's probably what I will do. So, okay. Should we just get going? All right, let's do it. Alrighty, so when we ended last time, we had just introduced the concept of partial pressure. And so we want to continue on with that a little bit. You may or may not know that the whole concept of partial pressure was introduced by John Dalton, the person for whom our Dalton lecture is named after. And through his work with ideal gas laws, he developed what is called Dalton's law, which is the law of partial pressures. And what it specifically states is the total pressure of a gas mixture equals the sum of the partial pressures that make up the mixture. So we went over that last time. We were talking about atmospheric air. So, you know, you get all the partial pressures of the gas of gases, you add them up, and they should add up to the total pressures. Okay. If we're going to work here, come on. All right, so if the gas composition changes, okay, then the partial pressures of all the gases will change. So if I add a new gas into the into the mix, then all the other partial pressures are going to change because the total pressure is fixed. It cannot change unless you do physically something to the environment to make the pressure change. Okay. So last time we looked at a cartoon diagram where you would compress a container. You can increase the pressure that way. But if we're talking about the atmosphere, the pressure is pretty much fixed at a given point in time. And so if you add a new gas into the mix, it's going to change the partial pressures of everything. Now, why is this thing being a pain? It's because I don't have it all the way pushed in. It seems to always be the problem. Okay. There we go. All right, so a classic example of this occurring is when you inhale air. So when you inhale air, your respiratory surfaces are all moist. There's all kinds of moisture in there. It's a very humid environment, and it tends to saturate the air that you inhale with water. So your lungs are adding water vapor to the air that you inhale. What this means is that water vapor then is going to have a partial pressure, which means it is going to dilute all the other gases because the pressure in your lungs is not going to change. So that reduces the partial pressure of everything else. It reduces the partial pressure of nitrogen, it reduces the partial pressure of oxygen, etc. And typically, when you inhale air, it adds about 47 millimeters of mercury of water vapor. So that would be its partial pressure. And since the atmospheric pressure, and actually the pressure in your lungs is actually a little bit lower than this, but for the sake of argument, we'll just call it atmospheric pressure, is a constant, then nitrogen, oxygen, carbon dioxide, their partial pressures are all going to be reduced. So how do we calculate what the new partial pressures are going to be? It's pretty simple, all right? So we take our atmospheric pressure of 760 millimeters of mercury, we subtract the partial pressure of the new gas that we've added. In this case, it's the partial pressure of water, and we get what's left, 713 millimeters of mercury. Well, if you take the water vapor out, all the remaining gases are going to be in the same portions that they were before the water was added. Does that make sense to everybody? So all you really need to go, you remember that nitrogen was 79% of atmosphere, just take 0.79, multiply it by 713, and you get the new partial pressure for nitrogen is going to be 563 millimeters of mercury. Oxygen, if you remember, was 20.95%. Multiply that by 713, and you get 149 millimeters of mercury. So it's a pretty simple calculation, as long as you know the partial pressure of the new gas that has been added to the mix. Are there any questions? That makes sense to everything. So partial pressures become important when we go up in altitude, because when we go up in altitude, the total pressure drops. And that's because that column of air that is pushing down on the surface of the Earth gets smaller. Okay, so the pressure becomes less as you go higher and higher in altitude. So if you go up to 9,000 meters, which is 25,000 feet, the total atmospheric pressure will drop to 282 millimeters of mercury. Okay, less than half of the total pressure at sea level. And so at 282 millimeters of mercury, the partial pressure of oxygen is only 59 millimeters of mercury. You can start to see how this will kind of play havoc with breathing. When you get to 17,000 meters, which is like, we're talking, you can look in the window of a jet plane. All right. Atmospheric pressure is around 50 millimeters of mercury. Well, remember what happens when you inhale air, it becomes saturated with water? Well, that 47 millimeters of mercury of water now takes up pretty much the whole gamut of pressure, and so you can't breathe when you get that high. You would need to have some sort of oxygen tank or something in order to exist at that elevation. This is why they have oxygen masks in airplanes if the cabin should depressurize. Because if they're up at this altitude, then air that's coming in is basically going to be oxygen free for you. In other words, no oxygen. Temperature is also important. So, Gay-Lussac's law basically says that if you have a fixed amount of gas, okay, you keep the number of moles of gas constant, and you have a fixed volume. Then, as temperature increases, pressure will increase as well. And this is a component of the ideal gas law, which you all learned in chemistry, right? So PV equals nRT. If we keep everything constant here, okay? If we keep everything constant over in the volume, N, which is constant anyway, R, and then all we vary is T, we can see that as temperature goes up, pressure is going to go up as well. And that's because the gas molecules have more kinetic energy. Does that make sense to you? All right. We're ready to switch gears a little bit. I can see those 3x5 cards filling up already. All right. Let's learn a little terminology associated with respiration. The first is what we call tidal volume. Tidal volume is just the normal amount, the normal volume of air that you breathe during a normal respiration. Okay. The tidal volume will vary with the amount of activity. So at rest, it represents roughly 12% of what we call your vital capacity. I'll define that in the next bullet point. But if you look at this graph right here, we have volume on the y-axis. We can see that at rest, we have a pretty low tidal volume. You know, our aerobic requirement is relatively low, so we don't need to breathe a lot of air. But as activity increases, you'll see we take deeper and deeper breaths, and so our tidal volume, the volume of air that we normally move when we breathe, is going to increase because our aerobic demand increases. Now, at rest, we say it's 12% of your lungs' vital capacity. The vital capacity is defined as the maximum air that can be expired after a maximal inspiration. So if we move over to this panel on your right over here, here you can see tidal volume. And then over here, you can see a maximal inspiration and a maximal expiration. The distance from here to here represents your vital capacity. Now there's a whole bunch of other terms that we can apply to lung volumes. So here's another graph that illustrates some more of them. So we have our tidal volume, which we defined in the last slide here. So your ability to increase tidal volume, okay? You know, how much can you increase it to accommodate your increased need for oxygen? Well, that volume is what we call the inspiratory reserve volume, and that is this distance right here. Okay, and that is defined as the amount of air in excess of tidal inspiration that can be inhaled with maximum effort. So when you take a deep breath, intentionally take a deep breath, you are filling your lungs up to the maximum accommodated by that inspiratory reserve volume. Okay, the expiratory reserve volume is the amount of air in excess of tidal expiration, okay, this bottom point down here, that can be exhaled with maximal effort. So when you push as much air out of your lungs as you can, okay, that is your expiratory reserve volume. Your residual volume is the amount of air, and that's this portion right here, that's labeled by number 4. That is the amount of air that is left in your lungs after that maximal expiration. And it's the amount of air that is necessary to keep your alveoli inflated between breaths, which is actually pretty important. So vital capacity, which we defined in the previous slide, but we can actually make a little equation out of it here. It is your expiratory reserve volume plus your tidal volume plus your inspiratory reserve volume. So it is this plus that plus that. Okay, and that is your vital capacity. Okay, and you can see that labeled with this arrow right here, number 5. Okay. Inspiratory capacity is the maximum amount of air that can be inhaled after a normal tidal expiration. Okay, so that is going to be number 6 here, which is right here. your inspiratory capacity. So it goes from so after you've expired during a normal tidal breath, the maximum amount that you can inhale. So it's going to be your inspiratory reserve volume plus your tidal volume. 7, your functional residual capacity is the amount of air in the lungs after a normal tidal expiration. So it is your reserve volume plus your expiratory reserve volume, or I should say your residual volume, pardon me, I call that the reserve volume, plus your expiratory residual or reserve volume. I'll get those oral words straightened out, I promise. All right. And so that's your functional residual capacity, and that's indicated by these arrows right here. And then finally, number 8, your total lung capacity is the maximum amount of air the lungs can contain, which is your residual volume plus your vital capacity. And so that's clear from the top up here to the top down here. So it's your vital capacity plus that residual volume here. So you can see we use a lot of terminology to describe the volume of the lungs in different ways. Does all that terminology make sense to you? All right. So one of the ways that we assess your respiratory performance is to measure what is called minute volume or minute ventilation. They mean the same thing, and one of your texts uses the term minute ventilation, and so you can use either of those terms. And it's simply equal to the tidal volume times breaths per minute. At rest, for a normal human, it's the minute volume or minute ventilation will equal roughly 6 liters per minute. Comfortable breathing, right there. Now, during exercise, tidal volume can increase, as we mentioned a couple slides ago. And so you can see as activity gets bigger, tidal volume gets bigger. And it can actually increase up to somewhere in the neighborhood about half your vital capacity. But your ability to compensate for aerobic need doesn't stop with just increasing your tidal volume. You also will increase your breaths per minute. The long and the short of it is you can go from a minute volume / minute ventilation of 6 liters a minute at rest up to a value of 100 to 200 liters per minute during intense exercise. So you can increase, depending on the individual, increase your minute ventilation by more than 20 times. And this is an indication of the respiratory system's ability to make adjustments for your aerobic demands, your need for oxygen. So when you are thinking about minute ventilation, though, tidal volume is really important. You can't just look at an individual and say, well, that individual has a minute ventilation of 6 liters a minute at rest, therefore they are doing great. Because that may not be true. And so this table illustrates 3 scenarios, which illustrate why this is the case. So let's take subject A here. The tidal volume is 150 mils. Breathing frequency is 40 breaths per minute. That equates to a minute ventilation of 6 liters. So your resting value. However, your alveolar ventilation with these parameters is 0. And the reason that it's 0 is because all respiratory systems have what we call anatomical dead space. That is the amount of air that resides in all the tubes that carry air into your lungs. And so when you have a tidal volume of only 150 mils, if your anatomical dead space is 150 mils, the only thing that you're ventilating is your anatomical dead space. No air is getting into your alveoli. So when we did the respiratory experiment, one of the experiments that we did was you extended the trach tube. Remember that? What we were effectively doing with that experiment was increasing the size of the anatomical dead space. So what do you think the response of the rabbit should have been when you did that in order to compensate? What did it need to increase? It's a level of silence. So let's look at subject B, and then I'm going to come back to that question. Here we have a tidal volume of 500 mils. Our breathing frequency reduced to 12 breaths per minute. We still have minute ventilation of 6 liters per minute. And now we have an alveolar ventilation of 4.2 liters. What's the difference? Yeah.
Are they taking like deeper breaths?
Yeah. They're increasing their tidal volume. So I will ask the question again. When you increase the anatomical dead space, what would be the predicted response, physiological response of that rabbit to compensate?
Increased tidal volume.
Increased tidal volume. Yeah, they should take deeper breaths. You would predict that they would take deeper breaths to overcome the increased anatomical dead space. If the goal is to continue with a normal level of alveolar ventilation. Look at case C down here. Now we increase tidal volume to 1 liter. We can decrease breaths per minute to 6. We still get 6 liters per minute ventilation. But now we have an alveolar ventilation of a little over 5 liters. So key point here is tidal volume does matter. This, subject A, really represents a case of hyperventilation, does it not? And we'll come back to hyperventilation in a minute. Questions? All right. There are some pretty common diseases of the respiratory system. Probably one of the simplest is what we call dyspnea. And this is just simply described as a feeling of difficult or labeled breathing. There are a zillion things that can cause this. Another that some of you may be afflicted with is asthma. Nasty little thing where you get constriction of your airways and it makes breathing hard. Okay. And so this is represented by some sort of an obstruction of airflow to the bronchioles. And interestingly, this is treated in a manner that simulates sympathetic stimulation because it's treated with drugs that have a similar structure to epinephrine. So they're related to epinephrine. And the reason for this is that it will cause bronchial dilation. Emphysema, common smoker's disease. Emphysema occurs when you have destruction of alveolar tissue in the lungs. So basically, you have fewer functional alveoli to absorb oxygen. Like I say, it is a common issue with chronic smokers. A disease that has similar symptomology is pulmonary fibrosis. Pulmonary fibrosis is a disease that is initially caused by the inhalation of these microscopic particles. This was the result of what we call black lung disease, where coal miners would inhale coal dust. And what happens is the body responds to that by building up these fibrous layers, fibrous protein layers, basically over the alveoli, reducing the number of alveoli that are functionally involved in respiration. And so the symptomology is going to be very similar to emphysema. Another cause of pulmonary fibrosis is asbestos. One of the big deals about, when you do a remodel on a place, they always do a test for asbestos in the walls, because you get that stuff flying around, it can drive this disease. When I had water damage in my den last year, when they came out before they did any work, they drilled holes in the walls and did an asbestos test. And my house was built well after the time that they stopped using asbestos, but the law requires them to do it. Okay, let's talk about what physiologically drives the rate of respiration. And we will focus primarily on mammalian values here, but it's going to center around changes in the values of PO2 and PCO2, so the partial pressure of oxygen and the partial pressure of carbon dioxide in the air and in circulation. So if you are breathing normal air, has a normal PO2, but the PO2 of your arterial blood drops below what is considered normal, that is an indication that there is some impairment of gas exchange. So this is why if you are thought to be having some sort of a respiratory issue, they will actually do an arterial blood draw and measure the PO2. Okay. Under normal circumstances, the PO2 in arterial blood is only about 5 millimeters of mercury below that of alveolar air. So they're pretty close. And something that is really interesting is that if you breathe 100% oxygen, it really does very little. It doesn't do nothing, because one of the things that does happen when you breathe pure oxygen is that it will increase the amount of dissolved oxygen in your plasma, and that oxygen can get delivered to tissues. But in terms of saturating hemoglobin, it really doesn't do a whole heck of a lot of good. And then the normal PCO2 value in systemic arteries or pulmonary veins is about 40 millimeters of mercury. These are human values. Let's talk a little diving physiology. There's nothing better to illustrate the importance of normal partial pressure, gas partial pressures, than looking at diving physiology. Any divers in here? I used to dive a lot, haven't done it in years. Done it in years, but when I took my training, they beat this stuff into me. Okay, so Physiological effects of abnormal partial pressures of oxygen and partial pressures of CO2 are illustrated in diving because the underwater environment puts you in a position to where total pressures can change quickly. So when you dive, going to a depth of 10 meters, so a little over 30 feet, will increase the total pressure by 1 atmosphere. In other words, it will double the pressure, which means the partial pressure of all the component gases of air are going to what? They're going to decrease, they're going to increase. They're going to increase by how much? If the total pressure doubles, what's going to happen to the partial pressures? They're going to double as well. I know, tough calculus. Okay. And so divers are really susceptible to negative consequences of having radical changes in the partial pressures of gases. So here are a few things that divers have to worry about. First one is what we call oxygen toxicity. Oxygen toxicity can occur when your PO2 gets abnormally high. So in the pulmonary system, when PO2 gets to be about 0.6 atmospheres, 456 millimeters of mercury, or in the CNS, when it gets to be 1.3 atmospheres or 988 millimeters of mercury, then you start to have problems. And you've all taken chemistry, so you know that a lot of oxygen does nasty things to other molecules. Okay, so you will start to oxidize enzymes, destroy any other protein that happens to be out there, and when you get afflicted by oxygen toxicity, it can kill you, put you in a coma, and yes, cause death. It's not a good thing. And this is the exact reason why when they fill a diver's tank to go diving, they fill it with atmospheric air. They don't fill it with pure oxygen. Okay? Because you wouldn't have to dive very deep in order to hit these numbers if you had pure oxygen in your tank. So you dive with atmospheric air, because then you have to go pretty deep in order to hit those partial pressure numbers. And you can look through the list of symptoms there. None of them are very pleasant. Now, at sea level or in our normal atmosphere, regardless, nitrogen is an inert gas. But put under high pressure, potentially not so much. So sea level, the amount of nitrogen in the atmosphere is physiologically inert, but under hyperbaric conditions, and that is defined as any condition in which the pressure is greater than 1 atmosphere. Increases in the partial pressure of nitrogen can cause a couple of different types of afflictions. One is what we call nitrogen narcosis. So this is something that divers who stay submerged for long periods of time can get affected by, particularly if they're diving really deep, so that the PN2 is really getting up. What can happen is this inert gas on shore turns out to be very intoxicating, and the symptomology resembles alcoholic intoxication. So divers can get disoriented. This is one of the reasons why they emphasize the importance of always diving with a buddy. So if you get disoriented, you have somebody there who can help you out. Okay. And if you get disoriented, you can become incapacitated. You can stop looking at how much oxygen is left in your tank. You know, a lot of things. And divers have died because of this. The common name for this is rupture of the deep, aptly named. Makes you all want to go out and play divers. Well, I will tell you, I have 2 diving certifications and worked hard to get them both. And I have watched so many people who go learn how to dive by a truck that backs up to a beach and dumps a bunch of equipment on the sand and says, put your fins on and go dive. You know, I mean, it's, there are too many physical things that if one is not comfortable understanding, they have no business doing that. Not the least of which is always never hold your breath while you're ascending. Do you know why? Yeah, because as you ascend, the pressure drops and that air expands in your lungs, and you can just imagine, you know, this big balloon in your chest just going pop. That wouldn't be very fun. Okay, another disorder that's associated with high PM2 is what we call decompression sickness. So when a diver dives deep, you get more and more nitrogen that's going to dissolve in your blood, and that's just because it's under higher pressure. If you ascend slowly, then that extra nitrogen, it will come out of solution. And if you ascend slowly, it'll come out of solution and be blown off via your lungs, via the alveoli. However, a problem occurs if you ascend too quickly. If you ascend too quickly, this nitrogen comes out really fast. It forms bubbles in your blood, which actually can block blood vessels. And this is what causes, you know, one of the common symptoms of this is joint pain. And that's because you get these blockages in your joints and it hurts. But if it blocks the wrong vessel, okay, if it blocks the wrong vessel, it can kill you. And the way that people get treated by this, and by the way, the common names for this is the bends, is places that are very popular diving locations will always have what they have called a decompression chamber. And so what they will do is they will take a person, they will put them in a decompression chamber and drop the pressure, or I should say increase the pressure, get that nitrogen back into solution, and then slowly let it out. That's the treatment for it. When I learned to dive, they were teaching what was called no decompression diving. It used to be in the old days that, you know, you would have tables and calculate, I'm down this deep for so long, so I have to ascend to a certain depth, and I have to stay at that depth for a period of time to allow the nitrogen to naturally blow off before I came to the surface. But when I learned, you learned what they call no decompression diving, which basically you were allowed to stay at a certain depth for so long without having to worry about getting the bends. And you just limited yourself to that much time so that you didn't have to worry about stopping anything. It's a little harder to do if you're diving really deep. All right, questions? All right, regulation of respiration. There are 2 primary receptors, types of receptors that are responsible for regulating respiration rate. These are the peripheral chemoreceptors and the central chemoreceptors. And I'll have to show you an image of these in a couple of slides. The peripheral chemoreceptors, they're found in the carotid bodies and the aortic bodies. And so they're associated with the carotids and the aorta. And they will respond to significantly decreased PO2. That will become important in a moment. So cases of substantial hypoxia. Increased hydrogen ion concentration. So in other words, if your blood becomes too acidic, and we refer to this as metabolic acidosis. Or if you have high PCO2, which also will make your blood acidic. Remember, you're going to produce all that carbonic acid. And that's what we refer to as respiratory acidosis. So that's the peripheral chemoreceptors. The central chemoreceptors, which are located in the medulla oblongata brain, so they're part of the CNS, they are going to respond to changes that occur within the cerebral spinal fluid. And this will be specifically associated primarily with changes in PCO2. And again, it's still going to represent a change in the acidity of the cerebral spinal fluid, because that CO2 is going to be converted to carbonic acid, et cetera. And that's actually what the receptors are sensing. So those are the two primary locations that are responsible for controlling the respiratory rate, and those are the things that they will respond to in order to regulate respiration. So, and I may have mentioned this before, but PCO2, not PO2, maybe that's surprising to some, is the primary regulator of respiratory rate in mammals, and that includes humans. So if we look at this graph right here, we can see minute ventilation on this on the y-axis, arterial PCO2 on the x-axis, and you can see there's a rather steep curve right here. That as PCO2 increases, you're going to be moving more air. Because that is an indication that you need more oxygen. When PCO2 goes up, you need more oxygen. That generally, in a normal individual, that would represent a heightened state of activity. All right, said that. All right. Here is a cartoon diagram which illustrates the central chemoreceptors as well as the ganglia in the medulla oblongata and the pons that regulate respiration. So if somebody has a traumatic brain injury that involves the brainstem, they often have respiratory issues because this is where your respiratory center is. And there's two primary regions. Up in the pons, you have what's called the pontine respiratory group here that consists of two primary ganglia. This pneumotaxic center right here, and this anoustic center right here. And these basically are kind of on-off switches for increasing and decreasing respiration. The pneumotaxic center will downregulate the activity of the respiratory center in the medulla here, and the apneustic center will upregulate. Both of these will interface directly with what's called the dorsal respiratory group right here. And the dorsal respiratory group directly innervates both the external intercostal muscles and the diaphragm, your two primary muscle groups that are responsible for respiration. You have a second ganglia up here, what's called the ventral respiratory group, that will innervate the internal intercostals and some other accessory muscles, a variety of other accessory muscles that assist in respiration. Okay. The regulation of the ventral group is primarily a function of what's going on in the dorsal respiratory group here. The dorsal respiratory group can be regulated by the pontine respiratory group up here. Does that make sense to everybody? And then these respond to the central chemoreceptors that are located in the brainstem. Questions? Here's a cartoon diagram that just illustrates the locations of the peripheral chemoreceptors. So they're found in the aortic arch here, and then also in the where the carotid bifurcates, going up into the internal external carotid. Okay. The peripheral chemoreceptors, if you remember back to the table I showed you a moment ago, they will respond to a greater number of things than the central chemoreceptors will, because the peripheral chemoreceptors will respond to metabolic acidosis as well as respiratory acidosis, and they are also responsible for responding to really, really low levels of oxygen. This here is just a diagram which just kind of illustrates the basic mechanism by which the central chemoreceptors are stimulated. We have CO2 that is flowing in the blood going to the brain. The carbon dioxide, or bicarbonate for that matter, will make its way into the cerebral spinal fluid, and it will ultimately generate a lot of free hydrogen ions, which is what will actually trigger the chemoreceptors. And the hydrogen ions are generated by the production of bicarbonate from that CO2. See that bicarbonate does a heck of a lot of things. I'll finish with this slide here because it kind of summarizes everything up. So here we have the central chemoreceptors here, so the medullary chemoreceptors that are going to trigger and upregulate respiration at the respiratory centers in the medulla oblongata. These will also interact with the carotid and aortic chemoreceptors as well, and you can get both just basic pH changes, so that would be a metabolic acidosis, as well as O2 that will fire via the sensory neurons, the afferent sensory neurons, which will go to the CNS and also trigger the respiratory group as well. One thing that we haven't talked about that can also stimulate the respiratory center and the medulla are emotions and voluntary control. I mean, you can just hear breathe as fast as you want, just by telling your brain, I want to breathe faster, because they are voluntary muscles. This will go through what's called your limbic system here, and these are nerves associated with the cortex that are basically tied to your emotions. You notice that if you get really emotional about something, your respiration rate goes up, and that's what drives it. And the last thing that I will say here is, I am going to highlight this. I'm not going to talk about it because I'm going to let you discover about it, but this is really important for your rabbit surgeons. Really important. You guys need to go and learn about the Herring-Brewer inflation reflex. These involve stretch receptors in the lungs and are really important when you are working with intact vagus nerves versus cut vagus nerves. Boy, that was a hint, wasn't it? Did you already discover it? No? Okay. All right. I'm sorry, I'm going a few minutes over time. Have a great day, everybody. Those of you in surgery, I'll see you tomorrow. The rest of you, probably on Monday.